ready to go small, like really small.
Small how?
We're talking subatomic baryons.
Oh, baryons. Those are...
The tiny particles that make up pretty much everything we see.
Right. I mean,
From us
yeah.
to the chairs we're sitting on,
Uh-huh.
to stars billions of miles away.
It's amazing to think.
Yeah, they're kind of the unsung heroes of the universe.
Absolutely. Fundamental.
And for this deep dive,
Yeah.
our guide is Jörg O. Schneeppert.
Oh, interesting.
And his essay,
Yeah.
Baryonen, Fundamentalteilchen in der Quantentechnologie.
I've heard of that, yeah.
It's a mouthful, I know.
It is, yeah.
But the insights, incredible.
Oh, I bet.
We're not just talking about what baryons are,
right?
but also their potential to revolutionize fields like medicine and computing.
I mean, that's what makes it so fascinating, right?
Exactly.
Yeah, these particles are fundamental to the universe.
Yeah.
But their applications could be groundbreaking, really.
So to kick things off, let's break down what Schneeppert tells us about what baryons actually are.
Well, at their core, baryons are subatomic particles made up of 3 quarks,
Okay.
held together by something called the strong force.
Okay, quarks and the strong force.
Mm-hmm.
Those are throwing me back to high school physics.
Oh, yeah.
Can we unpack those a little?
Absolutely. Imagine quarks like tiny building blocks.
Okay.
And the strong force is the superglue
Okay.
that holds them together.
Got it.
There are different types of quarks.
Yeah.
And depending on how they're combined, they form different baryons. It's like, you have a set of Legos
Okay, yeah.
where each brick has a unique property.
Right.
Yeah.
So protons and neutrons, the stuff we learned about in school, those are baryons.
Exactly.
Yeah.
Protons and neutrons are the most common baryons and the ones that make up the nucleus of an atom.
Right, okay.
Yeah.
And Schneeppert mentions this idea of baryon number conservation. What's that all about?
That's a key principle.
Okay.
Essentially, the total number of baryons in the universe is constant.
Okay.
So for every baryon that's created, an antibaryon is also created. And when they collide, they annihilate each other.
Oh, wow.
It's like a cosmic balancing act.
So even though these particles are constantly interacting and maybe even disappearing, there's an overall balance.
Exactly. Yeah.
That's pretty wild.
It is. It speaks to the incredible order underlying the seemingly chaotic world of subatomic particles.
Right.
But it's not just protons and neutrons out there.
Okay, Schneeppert hinted at some more exotic baryons, right?
Uh-huh.
I'm intrigued.
There are hyperons.
Okay.
Which contain strange quarks. And then there are these things called pentaquarks.
Pentaquarks.
Which are still a bit of a mystery.
Pentaquarks. That sounds like something out of a sci-fi movie.
I know, right?
What makes them so mysterious?
Well, their structure is completely different. Okay. They have 4 quarks and an antiquark instead of the usual 3 quarks.
Wow. It seems like every time we think we have a grasp on these particles, something new pops up to challenge our understanding.
Yeah.
What does the discovery of pentaquarks mean for our understanding of the universe?
It means we still have a lot to learn. Pentaquarks are pushing the boundaries of our understanding of how quarks can be arranged and interact.
Interesting.
Each new discovery like this refines our model of the subatomic world.
So we've got these exotic baryons and the more familiar ones.
Yep.
But where do they fit into the bigger picture? Schneeppert mentions some real-world applications.
Yeah.
And this is where it gets really interesting for me.
Oh, for sure.
How do these tiny particles make the leap from the subatomic world to things that can actually help us?
You're right. Baryons aren't just theoretical concepts. They're making waves in cutting-edge fields like quantum medicine and quantum computing.
All right. So how do those work?
Well,
how do they use these things?
Let's take proton therapy, for example.
Okay.
It's a type of cancer treatment that uses a beam of protons, which, remember, are baryons, to target and destroy cancer cells.
So it's like a super precise weapon against cancer. Using these tiny particles to fight the disease.
That's a great way to put it, yeah.
And how about...
And it's incredibly effective because protons can be controlled with much more precision than other forms of radiation therapy, meaning less damage to healthy tissue.
Wow. And then there's quantum computing.
Right.
Another field that seems to be exploding with possibilities. Where do baryons fit into that picture?
Well, there's a lot of research right now
looking
into the potential of baryons, specifically their unique interaction with the strong force, to build more stable and powerful quantum computers.
So baryons could be the key to unlocking the next generation of computing power.
It's a possibility that has scientists really excited. Imagine computers that can solve problems in seconds.
Yeah.
That would take classical computers years or even centuries to crack.
That's mind-blowing.
It is.
But all this makes me wonder.
Yeah.
If baryons are the building blocks of matter, and matter makes up the universe, then how did the universe come to have all this matter in the first place? Especially since Schnepp mentions that matter and antimatter were created in equal amounts during the Big Bang.
Oh, right.
Shouldn't they have just annihilated each other?
Yeah.
Leaving nothing behind?
That's one of the biggest mysteries in physics.
Yeah. What happened?
Right.
It's like setting off a giant explosion and then finding out that half of the explosive material just vanished.
The prevailing theory is that shortly after the Big Bang, there was a slight imbalance in the creation and annihilation.
Of baryons and antibaryons.
Interesting.
This tiny asymmetry, known as baryogenesis, led to the surplus of matter that we see today.
So it's like the scales were tipped ever so slightly in favor of matter, and that tiny difference made all the difference.
Yeah.
Wow.
And while we have some ideas about how baryogenesis might have happened, it's still a very active area of research.
It seems like with baryons, we're always teetering on the edge of the unknown.
It seems that way.
There's so much we know.
Yeah.
But even more that we don't.
That's the beauty of science, isn't it?
Yeah.
It's a constant exploration, a journey of discovery that never truly ends.
Right.
And with baryons, it seems like we're just getting started.
Well, I'm hooked.
Good.
What else did Schnepp cover in his essay that we should dive into?
Well, he digs a bit deeper into the characteristics of baryons, explaining that their properties are determined, not just by their quark composition,
but also by things like their spin, charge, and mass.
So it's not just about what kind of quarks they're made of,
right?
But also how these quarks are arranged and interact with each other.
Exactly.
Kind of like how the same ingredients can make a cake or a cookie.
Yeah.
Depending on how you combine them.
That's a great analogy.
Right.
And speaking of ingredients, remember how we talked about different types of quarks? Schnepp calls these different flavors. Like up, down, and strange.
Right, like different flavors of Lego bricks to build our baryons.
Exactly. And these different flavors combined with the strong force holding everything together lead to the incredible diversity of baryons we find in the universe.
Yeah. And a strong force is key here, right?
Absolutely.
Schnepp points out that it's one of the four fundamental forces of nature.
It is. It governs the interactions between quarks and keeps them bound within baryons. And it's also responsible for holding those baryons together.
Yeah.
In the nucleus of an atom.
Schnepp also talks about something called color charge.
Yeah.
But he makes it clear this isn't about actual colors.
Right.
What's the deal with that?
It's a bit of a head scratcher at first.
Yeah.
But essentially, color charge is a quantum property of quarks. It comes in 3 colors, red, green, and blue. Along with their corresponding anticolors.
All right, I'm starting to feel a bit lost in the quantum weeds here.
Sure.
What's the takeaway for someone like me who's not a physicist?
Think of it this way. Every baryon needs to be color neutral. Meaning it has to have 1 quark of each color. It's like mixing red, green, and blue light to get white.
So it's all about balance.
Yes.
Again, like that baryon number conservation we talked about earlier.
Precisely. Everything in the universe seems to strive for a kind of equilibrium.
Okay, so we've got our quarks with their different flavors and colors, all held together by this incredibly strong force.
Right.
It's starting to come together.
Good.
But I'm sure there's still a ton we don't know about baryons, right?
Oh, absolutely. Schnepp acknowledges that there's still so much to explore.
Like what?
For example, we're still trying to understand the exact nature of the strong force and how it gives rise to the properties we observe in baryons.
And what about those exotic baryons like pentaquarks?
Yeah.
What might those teach us?
They're potentially a window into new physics. Their unusual structure challenges our understanding of how quarks can be arranged. Suggesting there's still much more to learn about how these particles interact and bind together.
It's amazing how something so tiny can hold so many mysteries.
Right.
But let's circle back to that big question about matter and antimatter. Schnepp mentioned something called Sakharov's conditions.
Yes.
What are those?
Sakharov's conditions are essentially a set of rules that must be met for the universe to have developed a preference for matter over antimatter.
Right, so how did the universe break the symmetry?
Well, according to Sakharov, there are 3 key conditions.
Right.
First, there have to be processes that violate baryon number conservation.
So there are loopholes in that cosmic balancing act we talked about.
Exactly. Second, there must be violations of something called charge conjugation, C, and charge parity, CP, symmetry.
Right.
This means that matter and antimatter don't behave in exactly the same way.
So a little bit of cosmic unfairness is needed to tilt the scales.
That's a great way to think about it.
Okay.
And finally, these processes have to occur outside of thermal equilibrium. Things can't be perfectly balanced for this asymmetry to arise.
So we need a little bit of chaos in the mix.
Exactly.
To tip things in favor of matter.
These 3 conditions provide a framework for understanding how the universe could have evolved to be dominated by matter.
That's incredible. We've come a long way from those simple Lego brick analogies.
We have.
It's clear that baryons are much more than just building blocks.
Right.
They hold clues to some of the biggest mysteries in physics.
It's true.
And it's not just about understanding the past.
No.
SNEPAD also explores how baryons could be harnessed.
Yes.
For future technologies, particularly in quantum computing.
Exactly.
Yeah, we touched on that earlier.
We did.
But I'd love to hear more.
Sure.
What's so special about baryons in the context of quantum computing?
Researchers are investigating the possibility of using baryons as qubits.
Hold on, so instead of relying on things like superconducting circuits, we could be using baryons.
It's definitely a possibility.
Wow.
Baryons have some unique properties that make them potentially well-suited for this.
Like what?
For example, they're incredibly stable and interact with the strong force in a way that could lead to more robust and powerful quantum computers.
It's like we're talking about science fiction here.
It is.
Computers that can solve problems.
Yeah.
That would take classical computers millennia to crack.
Right.
That's wild.
It's definitely an exciting area of research. And while it's still very early days, the potential applications are mind-boggling.
It's clear that baryons are much more than just tiny particles. They're shaping our understanding of the universe.
Right.
And could hold the key to unlocking some incredible technology.
Absolutely. I think that's a great place to wrap up our discussion of SNEPAD's essay.
Yeah.
It's been a fascinating journey.
It really has.
Through the world of baryons. From their basic structure to their potential to revolutionize medicine and computing.
I agree. It's amazing how something so small,
I know, it's incredible,
can have such a profound impact on our understanding of the universe and the future of technology. Makes you wonder, like, what other incredible applications are just waiting to be discovered?
Oh, I bet. It really is an exciting time to be following these developments.
Yeah.
What stood out to you from all this?
Honestly, the sheer scale of it all just blows me away.
The scale.
Yeah. We started with these tiny particles, baryons, and ended up talking about the origin of the universe. Cutting-edge cancer treatments, and computers that could completely change everything.
It really highlights the interconnectedness of science.
It does, yeah.
From the smallest scales to the largest.
Right.
It all comes back to these fundamental building blocks.
And SNEPAD's essay, Baryonen, fundamental Teilchen in their quantum technology, does such a great job of capturing that interplay between the theoretical side of things and the practical applications.
He reminds us that science isn't just about abstract equations and complex theories.
Right.
It's about understanding the world around us. And using that knowledge to make a real difference.
I think one of the biggest takeaways for me is that we're still just scratching the surface.
Oh, yeah.
When it comes to understanding baryons.
Absolutely. There are still so many unanswered questions.
Like,
how did the universe end up with more matter than antimatter?
Right.
What other exotic baryons are out there waiting to be discovered?
Yeah.
And how can we harness the power of baryons to create new technologies that benefit humanity?
It's like we've opened a door to a whole new world, and we're just beginning to explore its wonders.
And who knows what incredible discoveries await us on the other side?
Well, one thing's for sure.
What's that?
Baryons are far more than just tiny particles.
I agree.
They're fundamental to our understanding of the universe. and they hold immense potential for shaping the future.
So the next time you look up at the stars, or marvel at the complexity of life, remember the tiny baryons that make it all possible?
That's a perfect note to end on.
It is.
This deep dive into the world of baryons have been truly eye-opening.
Absolutely.
Thanks to Yurgo Schneppet's insightful essay.
Yeah.
We've gained a newfound appreciation for these fundamental building blocks of matter.
And for listeners who want to explore further, I highly encourage you to check out Schneppet's work and see where your own baryonic journey takes you.
Until next time.
Yes.
Keep exploring.
Keep questioning.
And keep diving deep into the mysteries of the universe.
Absolutely.